afternoon.
Good afternoon, sir.
So, can you see my screen? So last time we were discussing the story of real numbers, and in this we found that there were natural numbers, then integers came into the picture, and then people thought that integers are not sufficient, then we should include some more numbers. Those are called as rational numbers, right? And then we found that there uh, are some numbers which are not rational numbers, right? Like root 2, root 3, and so on. This is what we were talking last time, right? So is it clear?
Yes, sir.
So very good. So now
Yes.
can you see this blank screen?
Yes, sir.
Yes.
Okay, very good. So uh, fine. So what we saw last time, we saw that. So just recall this. So natural numbers, subset of whole numbers, subset of integers, subset of rationals, right? So this was the last we saw. Okay, so we saw that there is no solution to the equation x square minus 2 is equal to 0 in rationals. Right, so what is the set of rational numbers? All the numbers of the type p by q. So p by q is just notation, right? So p, q are integers and q is non-zero integers. So p by q is a notation to denote some rational number. So why I am saying notation? Because suppose, as we discussed last time, suppose I have a bread, one bread, and I divide it into 3 equal parts, right? So what is the size of this part? Size of this part is a 1/3 of this, and how to denote 1/3 part? So this is a notation, right? This is a symbol, and the symbols, we are comfortable with these symbols in the current situation, so we are using these symbols. Otherwise, if ancient people would have defined some different symbols, we will be using some different things, right? So remember this. So this is a symbol to denote the 1/3 part of a bread, whatever 1/3 part of a unit quantity. Right, so there is no solution to such type of equation, or there are many such equations, lots of equations which do not have a solution, right? And then what we proved last time, uh, we saw that the number which is a solution of this equation is not rational. Right, so and I gave you exercises, many exercises, root 3, root 5, root 2 plus root 3. So there are many such numbers which are not rational numbers. Okay, so if you look at a right angle triangle whose sides are 1, then what is hypotenuse? What is the length of hypotenuse in right angle triangle? Root 2, right? And therefore, why root 2 or why such numbers came in the mind, right? People thought that if you put all the rational numbers on this line, real line, the line will be completely filled by rational numbers. And then people found that, oh, there are such numbers. Like what is the hypotenuse of this right angle triangle, right? What is the length of hypotenuse of this right angle triangle? So it is square root of 1 plus 1. And where is this number? And this number is not in rational. So people, like we saw the proof last time, the people proved that this is not in rational. So where is this? Because I have a length, whatever is this length, I have a length, right? So that means root 2 can be constructed. Constructed, that means we can actually construct, right? Suppose in your house you want to construct length root 2. Can you construct? Right, it is easy. You will just take draw a right angle triangle whose sides are 1 1, and then you will take a thread of length which equal to hypotenuse, that is a length root 2, and therefore you can actually construct at your home length root 2. Right, so such numbers are called as constructible numbers. Such numbers are called as constructible. Such numbers are called as a constructible number. So construct, you can actually construct. So there are numbers which are not constructible, right? So there are numbers which are not constructible. For example, that means, see, there are many types of numbers, but we are basically interested in this course, the real numbers, rationals and irrational. That is our main motive here. But there are, you can further classify different types of numbers. For example, we cannot trisect angle whose measure is 20 degree. So for example, if you have angle whose measure is 60 degree, certain you can trisect, right? 20 20 20, but it is not easy. So bisecting angle, suppose you have some angle, bisecting angle is a easy job, right? And you learn in school also, right? So how will you bisect? You take some compass and you fix some points with equal distance, and you mark here, and from this you mark here, and you join this. So you can bisect angles, and therefore you are given any number, you can find the half of it. It is exactly saying that can you bisect the angle, so it is easy. That is a construction, right? This is actually construction. So, but you cannot trisect all the angles. So some trisection of some angles is not possible. That means some numbers you cannot construct actually, right? So you may not understand all the details right now, but you can read further literature about such things, which has applications in algebra, general algebra. Okay, fine. Our main issue is root 2. There is a right angle triangle whose hypotenuse is root 2. That means we can actually construct length root 2. So is it clear? We can construct root 2. Right? Can you hear me?
Yes, sir.
Okay, very good. So that means such numbers are there which are not rationals, and we last time we have verified it, root is not rational. So we have a length root 2, but it is not in rationals. So thus, what is the conclusion of all above discussion? Thus there are numbers which are not rational numbers. So if we include, so such numbers are called as irrational numbers. And then people realize that there are numbers which are not rationals, right? And these numbers are reals, actually reals. Why reals? We can actually see in real life there is a length root 2. Right, it is nothing like imaginary, or it is nothing like fantasy, we cannot see, it is just fantasy kind of thing. So it is not a fantasy, it is a real, and so we can see such things. So therefore these are real numbers but not in rationals. So the set of irrational numbers of is denoted by the set of irrational numbers is denoted by q complement, and set of rational numbers is denoted by q. Thus the set of real numbers denoted by this special symbol. So you should remember this symbol, and this is not same as our usual R. Remember this. So you have to be very careful when using the symbols. So this is a special symbol for set of real numbers. It is not like our usual R. The set of real numbers is R is equal to rationals union irrationals. So it's a set of real numbers is a set of all rational numbers use union with irrational numbers, and then we uh, arrange all real numbers on a line. We can arrange all the real numbers on a line so that the line is completely filled. Right. So if we arrange all the real numbers on a line, right, then line will be completely filled under some assumptions. But how to arrange the real numbers on a line? Can we put arbitrarily numbers? Today I will put, for example, today I will put 0 here and -1 here and 2 here. So, so next time I will put 2 here. I will put 2 here and -1 here. So is it possible? Today I will put -1 here and 2 here. Tomorrow I will put 2 here and -1 here. Is it possible?
No, sir. No.
No, right? Otherwise, if you put in this way, then there will be the system will collapse, right? And the entire world will collapse because everything will be disturbed. So this is not true. And what is the rule? Why -1 is kept here and why 2 is kept here? Why 0.5 minus 0.5 is here and why 1.7 is here? So why? What are the rules? Right? So these rules are called as axioms, right? Axioms, and we are going to learn all these axioms. So to understand structure of system of real numbers, right? To understand structure of system of real numbers, we need to understand all the axioms which are there, all the axioms or rules which are there on real numbers, right? So and what are the axioms? So certain axioms are there that we'll discuss later on one by one. Right. So far everything is clear. See what we are doing. So this is a story, and you need to understand it is like a story. How we are developing our story. So we now believe that there are numbers which are not rational numbers called as irrational numbers. Combine all such numbers together with rationals, that constitutes the set of real numbers. That's it. But then the story is not stopped here. Further, people found that there is no solution to the equation x square plus 1 is equal to 0 in real numbers. Still real numbers were insufficient due to some reason, because further people tried to solve some real life problems and they came across such equations whose solution is not real number. Right. For example, if alpha is a solution of x square plus 1 is equal to 0. Suppose alpha is a solution of this equation. Then what will happen? Alpha square plus will satisfy this equation. That means alpha square is equal to minus 1. Right. That means therefore square of alpha is minus 1, which is negative and which is a contradiction. Why contradiction? Because square of uh, or contradiction, or what I can say, alpha is not real number. So square of alpha is negative. So therefore alpha is not real number, because square of every real number is positive. So because of real number is positive, or every real number is greater equal 0, or non-negative is non-negative. Again, why? That is a question. Why square of every real number is positive? So we are going to find answers to such questions. Why? Right? Why minus 1 is negative? Why square of real number is non-negative? So there are lots of questions, and that is the basic structure of real numbers. And we want to understand this basic structure, right? So what is our aim now? Aim is clear. We want to understand basic structure of real numbers. Why all these things are there in real numbers? And therefore, people thought that again, real numbers are not sufficient. Include such numbers, right? So therefore, alpha is not a real number, and alpha is square root of minus 1, not real. So called as imaginary number. Denoted by root minus 1 is equal to I. I stands for imaginary. So the number square root of minus 1 is denoted by I, and then the set x plus iy, where x and y real numbers, is called as set of complex numbers. And this set is identified with, for example, x plus iy is identified by the pair xy in plane, right? And that is the different story that we learn later on while studying complex numbers. But right now we are interested in real numbers, right? So the story is not finite, or story is not stop at story doesn't stop at real numbers. There are further developments in systems, number systems, right? That one further step is a complex numbers, but and after that also there are some more developments if you study higher mathematics. Okay. Fine. So okay, so real numbers. Okay, so up to this, is it clear? Everything is clear. So far everything
Yes,
is
sir.
Yes, sir.
okay. Very good. Now what is our aim? Our aim is a big aim. And what is our aim? To understand the structure of real numbers, real number system. Right, so this is our ultimate aim. What exactly these real numbers are. You are already using the real numbers since your school, but you did not bother about what this structure is, right? And now after you studied lots of things about real numbers, and then you are bothering about what is that basically structure is, right? So anyway, so we want to understand what is the structure of real numbers. So in this process, my first step is binary operation. So binary operation. So suppose A is a set. A is a set. Then all of you know what is the definition of function. Do you know definition of a function? Anybody know definition of a function? Nobody knows definition of a function. You know definition. Have you heard this word function, map?
Yes, but I don't
Yes,
know
sir.
exactly what is the definition of it, but I can explain a bit that when from one set to another set we make a relation, then a function is always the first. I can't explain, sir. I just know what is function, but
A
I can't.
function is always a one-one on onto relation between two sets.
No, not necessary one and on to. Okay, let me tell you what is a function, then we'll go further. Okay. We'll come to binary operation later on. So let me first tell you what is a function. Okay, so function.
Function is a relation between two sets where one set the elements
Ah,
have exact pre-image the other set.
so uh, suppose, let me tell you the precise definition, then you can understand it. Suppose A and B are two sets. A and B are two sets. A function uh, from set A to set B is a relation such that every every element of A is related to unique of B. Every element of set A is related to unique element of B. And here, while talking about function, when we say function, then these two words are very important, every and unique. Right, so every and unique. Every and unique. Why these two? Unless understanding these two words, you cannot understand function at all. So let me explain why these two words are important. Okay, suppose my set is this A, B, C, three elements here, and this is my set B. 1, 2, 2, 3, 4. Now I am relating A with 1. I will relate B with 2. I will relate C with 3. Fine. Now this is one relation. Another relation I am defining among two sets. This is my set C. This is my set D. And I have suppose here P, Q, R, and here some box whatever is here, some triangle here, and some circle here. Doesn't matter what are the objects. Sets are what? Collection of objects. So, and therefore no matter what are your objects. I can have objects of stones, objects are stones or some shapes, whatever. Okay, so I will relate P with this square. I will relate P with triangle also. I will relate Q with this, right? And I will relate this with triangle. This is second situation. Now third situation. I have set P, I have set Q, and here I have some I have some cow, here I have some elephant, or here I have some lion. Doesn't matter what are the objects. Suppose I have here some apple, I have suppose banana, I have suppose pomegranate, and suppose I have some guava. Whatever are fruits, doesn't matter. Now I will relate this with this with this, right? Third situation. Okay, so all these are relations now. Am I right? All these are relations now. But which relation is a function? Which relation is a function? Every element of A. Every element of A must be related to unique element of B. So for in first situation, A is related to something, B is related to something, C is related to something. So every element of A is related. First thing, every is clear. Am I right? Okay. Now second condition, unique. Every element is related to unique element. So A is related to one, unique. One is unique, right? B is related to 2, which is a unique guy here. C is related to 3, which is a unique object here, right? Okay. So therefore, every and unique, both conditions are satisfied. Therefore, first situation is a function. Clear. Now go to the second situation. So P is related to square, and P is also related to triangle. Q is related to circle, and R is related to triangle. So first condition is okay. Every element in this first set is related to something, that is okay. First condition is clear. But what about second condition? Is unique? The elements are related to unique element. Is unique? P is related to two different objects, square as well as triangle. So uniqueness fails, right? That is not an issue. P and R are related to same object. That is not an issue. But the issue is every element is related but not unique. So unique fails. So this is not a function. This is not a function. Fine. Now third situation. Is first condition satisfied? C is related to A.
No. Yes.
Every fails, right? Because every element should be related to some element here, that fails. So first condition itself fails. More or second condition is fine. Unique, C is related to unique element and E is related to unique element, that doesn't matter. But every element is not related, so that fails. So this is also not function. So let me tell you another situation, X and Y. So A, B, C, D, E, 1, 2, 3, 4. Okay, so I will relate this. Okay. I will relate D with 2 and E also with 2. Okay, so this is fourth situation. Is it a function?
Yes.
This is also a function because choose verify first condition. Is every element related? Yes. Right? Every element is related? Yes. Is every element related to unique element? Yes. A is related to 1.
No.
Right? A is related to 1. A is not related to any other element, so A is related to only one element, so uniqueness is true. B is related to one unique element, right? It is not, doesn't matter that two elements are related to same thing, that is not an issue, right? But what is our condition? Is every element of first set is related? Yes. Is every element related to unique element? Yes. Right. So this is a function. Remember this. Right. So where you come across such situations, where you come across functions in real life, right? Suppose you have computers and you have servers, right? So first set contains computers, second set is server. Then you can connect many many computers to same server. That means we are assigning computers to the server, right? So there are lots of situations where you come across the functions. Right, suppose I have caps and students. I want to distribute all the caps. What I will do? I will give one cap to each student. Right, this is a kind of function. So, and therefore now definition of function is clear. Definition of function is clear. Is it
Yes,
clear
sir.
now?
Yes, sir.
Yes, sir.
So very good. So definition of function is clear. Now I will tell you further about function. Okay, so if f is a function from A to B, it is denoted by this notation. F is a function from A to B. So what does it mean? F is a function from A to B. So for x belongs to A, if x is related to y in B with respect to function f, then we write it as, right? So when we say that f from A to B is a function, and suppose some object is related to some object in B, then then we write it as fx is equal to y. What does it mean? Y is related to x with respect to function f, with, right? Y is related to x with respect to this function. Correct? So this is how we define, we make the notations. Okay. So for example, if I define f from R to R and f of x is equal to root x, then is f a function? Is f a function? If I define f of x is equal to square root of x from real numbers to real number, is it a function? Very elementary question, trivial question. So is it a function?
No, sir.
No. Why?
Because root of
Because it
minus
can't be
1
negative values.
So which condition in definition of function fails?
F3.
So for every
That means
fails.
domain should be different.
For every fails in this case, right? Right, for every fails, because for x is equal to -1, f of x is square root of -1 is not available in codomain, not
Yes, sir.
available in the second set, right? And what our condition or definition, for every element in A, there should be a corresponding element in second set. But for example, for -1, the f of -1 is not there. F of x means what? F of -1 is not available in R. That means corresponding element is not available with respect to this kind of relation. So this is not a function. Right. So not a function. So not function. That is clear. And therefore, only giving expression or formula doesn't mean that it is a function. So you should think about what is a domain and what is codomain. But if I define G from positive real numbers, x such that x positive to R, and f of x is equal to root x. Now, is it a function?
Yes, sir.
Yes,
Yes, sir.
because no problem. You choose any number from positive real numbers. Certainly, the square root exists, right? So this is a function. Therefore, if you change domain or codomain, it depends on your domain and codomain. So let me note this. So if f from a to b is a function, then set A is called as domain of f, and B is called as codomain.
Range. But in example, if we change codomain as complex number, it also can be valid.
Very good. So for example, if you define h from R to C and hx is equal to square root of x, then clearly it is function, right? So therefore it depends on what is your domain and codomain. Only formula doesn't make sense, right? Only formula doesn't make sense. You should think about what is a domain and what is codomain, then only you can confidently say that whether it is a function or not. Fine. So but what is the range of function? Range of function f,
Sir, all values of y.
not all values. Okay, so
Subset of codomain.
so in first case, in our first example, ki ABC 1 2 3, what is the range here? What is the range? B is codomain, no doubt, but range is
Elements of set A. 1 to 3.
1 2 3, right? 1 2 3 are in the range. 1 2 3 are the only in range. 4 is not in the range, right? The range of function f from A to B is the set Rf, range of f, or range of f is the collection of all images, right? That means you choose any element from A, apply function f, whatever you get, put that in the range, right? So it is like a gun. Suppose you have a gun and you have bullets, right? So this is box containing bullets and you have a gun. So you take a bullet and fire by a gun, it will go somewhere here. You take another bullet, fire by a gun, you will get here. So wherever bullets hits, that is the range, right? So wherever your bullets hit, that is your range. Outside it not in the range, correct? Outside the range. If you choose any point in outside the range, there is no bullet which can be fired at this point. Right, so outside the range. So that's why the word range is used here. So range, where function can fire the elements. Right, so function is like a gun. You take a bullets as a domain and you fire. What is your codomain? You have a bullet and you are standing at some point and you are firing bullets to your entire space is your codomain. But how far you can fire the bullet? That is the range. Not entire space is your range, right? So therefore, if I define function f from R to R, fx is equal to x square. Fx is equal to x square, right? So domain is real numbers and codomain is also real numbers. But if you choose any real number and apply this function, we will get square, and all squares are on positive side only, right? All squares are on positive side. So for every x in R, that means for every bullet in domain, if we apply function, what we get? The square, and square is always greater equal 0. Right. Therefore, if you take bullets from this set and if you fire by this gun, now our gun is this fx equal to x square. If you fire these bullets by this gun, where it will hit? It will hit on positive side. No bullet is there which will hit on negative side. Right, and therefore what is the range? So range of this function is positive side, 0 to infinity. Is it clear? Is this clear?
Yes, sir. Yes,
Okay, very
sir.
good.
Yes, sir.
Fine. Now you can understand what is a function. So definition of function is clear because it is very essential and we need it at several occasions. Right, and you should read Bartle book that I suggested you and read all about the functions. Right, so that your concept will be clear. That will be helpful in algebra as well as calculus also. Fine. But what was our basic aim? Binary operation. We are talking about binary operation. Binary operation. So binary operation. So let A be a non-empty set. Suppose A is a non-empty set. A binary operation okay, binary operation I will denote it by star for this instant. On A is a function star from A cross A to A. That's it. What is a binary operation? Binary operation, this is a notation for my binary operation star, is a function from A cross A to A. What does it mean? It takes element from A cross A and it gives some element in A itself. Now you know the definition of function. Okay, let us see example, then you can understand it. Let A is equal to set of real numbers and I will define star. Now what is A cross A? A cross A is R cross R, but R cross R we denote by R2. And what is R2? Plane. All of you know the what is the meaning of R cross R? By Cartesian product, X and Y are from real numbers. Is it clear? What is R cross R?
Yes, sir.
Right. Cartesian product of R with R. And by definition of Cartesian product, what is R cross R? Pairs. And what are the pairs? First element is from R and second component is from R. But both are same R. Therefore, both x, y are real numbers. So this is clear. What is R cross R? And therefore, I define a star from R cross R to R. What is my binary operation? Star of xy is equal to x plus y. Is it a binary operation? Is it a function? Is it a function? Is it a function?
Yes, sir.
Yes, because when I say that key it is a from R cross R to R, can I apply this operation or this function on every element of R cross R? Yes, that means you choose any x and y and you can add them. Is it possible to add two real numbers? Certainly yes. So for every is clear, every condition is clear. Unique, that means if we add two real numbers, can we get the unique number? Right? Is it clear? What is star of 2 comma 3? What is action of this function on this element 2 comma 3? What is action?
5.
Right, very good. 2 plus 3 is equal to 5. So what is action of 0 comma 1? Action on 0 comma 1, 0 plus 1, that is 1. That means if we apply this function on any element in R cross R, I will get unique element. Right? I will get unique element. So therefore clearly star is a function. Clearly star is a function. Am I right? So we denote here, we denote the star by plus, star by plus. Thus, if we apply plus on 2 comma 3, what I will get? 2 plus 3, which is 5. Right? What is it clear what I am saying? This is a logical fact. Is it clear?
Yes, sir.
Very good. and therefore usual addition is a binary operation. Thus, usual addition of numbers is a binary operation. So that means we add two numbers when we perform addition. What we need at least two numbers, right? So can you perform addition using only one number? Correct? My question is clear. Can you perform addition if you have only one number?
No,
No.
sir, we can't.
Right. Therefore, if you want to perform operation addition, we need two numbers, and we need two numbers. We need pair. We need pair, and once we have a pair, we can apply the operation addition. What is operation addition? Just add these two numbers, right? And therefore, addition is a binary operation, or addition is a function from R cross R to R. That means if we apply addition on pair x comma y, we get x plus y, which is a real number again. This is what the story is. Similarly, if we define the dot from R cross R to R by dot of xy is equal to x dot y, right? What is this? Usual multiplication. Usual multiplication. Is it a binary operation now, multiplication?
Yes.
Yes, right? So if you want to multiply, if you want to apply a multiplication, you need two numbers. That means you need a pair, and then on that pair we can apply multiplication. So multiplication is again a binary operation. Thus, what is the moral of the story? The usual addition what is usual addition? We denote by the symbol. This is a symbol. When I say symbol, then it is a symbol which the people give for addition for our convenience, for our communication. Otherwise, you can use your own symbols, but for understanding and for communication, these symbols are universally accepted, right? The usual addition and usual multiplication, right? Dot usual addition, right? I'm mentioning it in the code because so usual addition and usual multiplication dot are binary operations on set of real numbers. Fine, right? So binary operations. So any doubt so far? Is the concept clear? What is a plus and what is dot now?
Yes,
Yes, sir. Yes,
Very good. Okay, and now using this plus and dot, we want to explore the set of real numbers. Uh, we want to go into inside the set of real numbers, and we want to understand it in very deep manner, very philosophical manner, right? So once you understand what is a plus and what is a minus, what is a dot, again minus is nothing different because what is uh, 2 minus 3? 2 minus 3 is 2 plus of minus 3, and minus 3 is a 2 is a real number and minus 3 is a real number. Basically, it is addition, correct? Therefore, there is nothing like it subtraction. Subtraction is a basically addition of two numbers, right? Or when I say division, x by b, x by y is basically x multiplication with y inverse, and therefore division is basically multiplication. And therefore, there are only two basic operations, addition and multiplication, right? So there are only two basic binary operations, addition and multiplication. Subtraction and divisions are not different from these two operations. They are same. right? Fine. So uh, thus the set of real numbers is equipped with two binary operations, plus and dot, right? So set of real numbers is now equipped. Now these are equipments for set of real numbers, and then we can handle the real numbers using these two operations. So now denoted by as r plus dot. Now these are two powerful tools or equipments with real numbers ki plus and dot, addition and multiplications. Right. So, and therefore we want to study very important, essential, fundamental properties of real numbers. So, algebraic properties of set of real numbers with these two important tools, addition and multiplication. Algebraic properties. Algebraic properties means what, or also called as field axioms of R plus dot. Now R is equipped with two operations, two important tools, addition and multiplication, and axioms. So what is the meaning of axioms? Axioms means rules, right? Building blocks. Right, what are the axioms? Axioms means rules or building blocks of structure of real numbers. Right, so when we define this, when people defined, ancient people defined or mathematicians defined the structure of real numbers, then they defined these building blocks also, right? These building blocks are not coming from any other property, right? Like as I told you, ki suppose you go to the college, you take admission, then what is your assumption? There are classrooms, there are teachers, there are blackboards, there is a principal and so on, right? There are peons, whatever. So these are axioms, assumptions. Without these assumptions, there is no college at all, right? Or you, if you imagine some institute or something, right? If you imagine if you want to construct some house, there are some building blocks. You have bricks, you have sand, you have cement, whatever. These are assumptions. So if you are talking about system of real numbers, these axioms must be there. These are the rules defined by ancient people, right? And then we are conveniently using these rules, these axioms in day-to-day life. Without this axiom, this set of real numbers is useless. Not of use. It is not useful for us, right? And what are these axioms? Okay, so what are these axioms? So first axiom, I can say it is A1. Why A1? That you can understand. So for xy in R, x plus y is real number, right? So closed under addition, closed under addition, plus or addition. So what is the first axiom says? You choose any two real numbers and add them. The new number, whatever new number will come out, that is again a real number. Am I right? Is it clear? Suppose you take 2 and 3 and add them. What I will get? 5, and 5 is also real number. Right? So no matter what real numbers you select. Suppose somebody will say that okay, real line is very big and 0 is here, and I will choose some number which is 100 kilometers away from 0, and I will choose another number y which is 1000 kilometers away from 0, and I will add them. And how can I check that it is in real numbers? Because the sum is very big. How can I say? right? But we have to bring it into the real numbers. In that way, you have to extend the set of real numbers and you have to make it very bigger and sufficient, right? So you choose any two real numbers. It is assumed that their sum is also real number. That is assumed. Assume means what? You have to bring all such numbers. If you add and then whatever new number, add in. Put in the set of real numbers. Take any two real numbers, add them. Whatever new number you will get, put in the real numbers. In this way, make your set very sufficient so that if you take any two real numbers, then add them, then you will find the sum is available in the real numbers. That is what the assumption is. Uh, Addition, it is closed under addition. Closed under addition means what? Closed under addition means choose any two real numbers, the sum is there. Fine. For xy belongs to R, x plus y is same as y plus x for any x and y. That is commutativity of addition. Of addition. That means addition is commutative. That means you either add 2 plus 3 or 3 plus 2 is same as 5. Right, so 2 plus 3 is same as 3 plus 2. Therefore, doesn't matter which elements you take first and which you take second. So that is true, that is assumed. Otherwise, if this condition is not there, then today I will give you 2 rupees plus 3 rupees, 5 rupees, and tomorrow I will give you 3 rupees plus 2 rupees. Then amount will be different. Then there will be lots of problems, right? Because of this axiom, we are happy in our day-to-day life, because otherwise situation would be very complicated if this will not be equal. Remember, there are many situations where these two things are not equal, that you can learn later on, but in real numbers this is true. Fine. A3. For you choose any three real numbers x, y, z, we have x plus y plus z is same as x plus y plus z, associativity. Right, so this property or axiom is called as associativity of addition. That means when you are going to add three numbers, first add two numbers, and then in that addition, because addition of x and y itself is a number, in that number add third. It is same as add two second numbers, second and third number, and in that addition whatever new number it produces, then in that number add first number. It's same, and that you experience every day. This happens to be true, right? So there exists a real number, very special real number. Let us call it as E, such that x plus E is equal to E plus x is equal to x for every real number x R. Right? Does there exist a real number which added with every real number gives same number x? Do you realize such number in the system of real numbers?
Yes, sir.
So what is that number?
Sir, 0.
Zero.
Very
Zero.
good. So the E is called as
Identity.
additive identity,
Additive identities.
and is denoted by 0, very special symbol 0. Right, so what is identity? Additive identity 0. Thus 0 plus x is x plus 0 is equal to x for every real number. Fine. Now for every, you choose any real number, there exists y, another real number, such that x plus y is additive identity. So this is called as existence of inverse. Right, so you choose any real number, I can produce another real number. If you added them, the sum is 0, right? So that is true in case of real numbers. So here y is called as additive inverse of x and is denoted by minus x. Thus, x plus y is 0 implies y is minus x. So how can I say that y is minus x? Because x plus y is 0 means y is additive inverse of x, and additive inverse of x is always denoted by minus x, right? And therefore, what is a minus x? Minus x is a symbol for additive inverse of x, not any special meaning to minus x. You can have some other symbol for additive inverse of x, but this is universally accepted, and communication for our day-to-day communication, this is convenient, so we are using minus x. And therefore, what is additive inverse of 2 is minus 2, right? So minus 2 is a symbol for additive inverse of 2. That's it. Okay, so there are more properties, but I think time is over, so tomorrow we'll continue from this. And you should just go through the book that I told you, Bartle book, and read that book. Then you can understand more about it, and next time we'll see further properties, and we try to understand the structure of real numbers. Okay, so fine. Any doubt?
No, sir.